Welcome, everyone, to our nerdy community of history buffs, where we are fascinated by the intrinsic human desire to create and to build. Construction history encompasses the investigation of all historic aspects of the built environment, including buildings, structures, builders, architects, engineers, contracting, and construction materials and methods. It addresses diverse and previously unexamined methods, techniques, practices, innovations, and whether small scale or broadly defined, local or international in scope. We've been offering these podcasts since COVID, to spread our scholarship and practice to a wider audience, which is you. Well, I am Peter Hilger. I am faculty director of the construction and real estate program at the University of Minnesota, a former board member of Construction History Society, former chair. I'm still a board member, I'm sorry. And today I'm behind the black curtain is Grayson Simmons, as he's actually operating the controls of this webinar. So thank you, Grayson, for doing that. I also want to introduce Alicia Svensson. Alicia, wave your hand. I obviously see you. She is a PhD candidate from Northeastern University, a board member, and one of my faculty members that will be teaching our construction history class online. That was previously taught by Brian Bowen, who is the founder of the Construction History Society, and who is our inspiration and leader of having developed this interest in construction history nationally in North America. Alicia will monitor your questions in the Q&A session and bring them up as needed. So, but wait, there's more. At the end of our two presenters, we have a really special surprise, a birthday surprise of over 200 years. So we'll bring that at the end. So hang in for that part of the presentation. So we're going to start today with Eric Bellin. Eric is an assistant professor at Thomas Jefferson University, College of Architecture and the Built Environment, where he teaches courses in architectural design, representation, and history. He earned his MArch from the University of Florida, practiced for several years in Miami, and then attended the University of Pennsylvania, where he earned his PhD in architectural history and theory. Eric's research is focused on 19th and 21st century histories and theories of building practices at the intersection of design, construction, technology, disciplinarity, and culture. He is the author of Detailing Worlds, a conceptual history of architectural detail published by Bloomsbury in 2025. Shameless promotion right here. That's the book. All right. He is also the editor of Weiss Manfredi's Drifting Symmetries, Projects, Provocations, and Other Enduring Models by Park Books 2025. So Eric, take it away.
Can everyone see my screen okay? Yeah. All right. So, hi everyone. Thanks for coming. And thanks also to CHSA for providing the opportunity to share some of my research with you. So today, I'll talk about one particular detail of the Crystal Palace, the famed iron and glass building constructed in London's Hyde Park for the 1851 Great Exhibition of All Nations. And the detail I'll discuss is one centered on a particular building component, so it's a part that the project designers simply called the connecting piece. And the sheet of drawings you see, here's a more properly legible version. So the sheet of drawings is from a book published in 1851, which collected illustrated plates of the building's technical drawings, which were transcribed, quote, from the working drawings of the contractors, Fox, Henderson, and Co. And here, this in the corner is the connecting piece, seen in elevation and correlated plan. And the sheet as a whole illustrates the many different ways in which it was used to connect vertical and horizontal structures, so columns and girders within the building's structural fabric. And so today, I'll explain and unpack this one detail of the Crystal Palace, a detail centered on the connecting piece. And I'll aim to show how this one detail reveals the ways in which the project's designers conceived, or maybe reconceived, of the building less as a singular discrete object and more as a system itself. And so I'll tell the story in three parts, beginning with some background on the building. So for those who might be less familiar with the Crystal Palace, it was built in London's Hyde Park for the 1851 Great Exhibition of All Nations, which was a sort of World's Fair of industry and material culture. And the building was massive. Its interior was over 100 feet tall at its highest point, and it was built right over collections of mature elm trees. And the building was essentially a showroom for goods. So, machines, furniture, decorative arts, crafts, all sorts of things from around the world. More than 40 nations had goods on display. Of course, this was the time of colonialism, so there's a darker side to this, but that's for another presentation. As for the building itself, at this time in 1851, it was the largest building to have been constructed of iron and glass, and by magnitudes. It contained almost 1 million square feet of interior galleries on a 700,000 square foot building footprint. So for comparison, at this point, the other largest iron and glass constructions had been about 40,000 square feet. And even more amazing is that the Crystal Palace was imagined, designed, fabricated, and assembled in well under a year. And honestly, depending on how you count, you could even argue that, in fact, it took just over 6 months from design to the completion of construction. And also key was that the building was temporary. So it was to be set up for the event and then disassembled after, which I'll get to a bit later. So the vision for the Great Exhibition Building was sprung from the imagination of Joseph Paxton, who was a gardener who was credited as the building's architect. He built a few glass conservatories with the assistance of an engineer. And his idea for the Great Exhibition Building, as you can see here on the left in his first sketch for it, was based on the repetition and extrapolation of a lily house he'd built the prior year. And he produced this drawing as a more formalized proposal, but at the time this was drawn, this is June of 1850, the opening of the event was just 11 months away in May of the following year, and Paxton had no idea how the project could actually be built in that time. So with his lily house, joints between iron members were secured with molten iron, and other components were all handcrafted. And this tiny project took more than a year to complete. So joints like this one would need to become something far more complex to achieve the expanded scope and speed necessary. And this is where the engineers come into the picture. So on the same day, Paxton formally submitted his proposal for the exhibition building. He also met with the civil engineer Charles Fox of the firm Fox, Henderson & Co., who agreed to collaborate on the project's detailed design, manage all fabrication and production, and serve as contractor overseeing all on-site work. And so over the next few weeks, Paxton and Fox met with glass manufacturers, other engineers associated with Fox, and architects, and the project was refined in a number of ways. So most obvious was the addition of the arched transept at the center of the building, but there was also a careful redefinition of dimensions for the building's structural module, which was based on efficiency of fabrication. And once the scheme was accepted, based more or less on the schematic drawings you see here, the project was set in motion. Now, at this point, Paxton was, and these are his own words, quote, obliged to leave England for a month on other business. And so this was mid-July. The building needed to be completed by January for the exhibition to open on time, which meant a lot of work remained to turn these very schematic drawings into the largest and most complex construction of iron and glass in human history in 6 months. So about this, Charles Fox commented that at this point the drawings, quote, did not contain either sufficient architectural or mechanical detail to admit of their being used in the execution of the works, end quote. So at this time, and in the absence of Paxton, Fox began to work 18 hours a day for 7 weeks to flesh out the project in detail. In his own words, quote, making every important drawing of the building is constructed with my own hand. With a small team of engineers assisting him, loads were calculated, parts were dimensioned, and connections were designed, yielding the comprehensive set of technical documents from which the building was actually produced. Basically, a full set of construction drawings for the building with the level of detail you see here. And it can be argued, and I certainly do, that this involved a large part, if not the majority, of the building's actual design. And further, Fox and Henderson would go on to manage all of the Crystal Palace's phases of manufacture. They forged and fabricated all the ironwork at foundries they and their associates owned or operated, and the same was true for all lumber and millwork. Fox and Henderson's team not only manufactured all the building components, but also handled logistics, prefabrication, managed on-site labor of thousands of workers in 3 shifts working 24 hours a day, and Charles Fox himself served as on-site contractor. And in the course of all this, their team invented scores of new machines and tools to economize work. They managed labor in ways wholly new to construction sites, and they mechanized building practices in ways that wouldn't be matched again for decades. They developed new apparatus and methods for materials testing to ensure the safety of what they were constructing. There was a lot of public concern about the safety of this completely new sort of building. And in fact, despite the building's scale and complexity and that the structure is made of all these custom components, they completed the building and had it ready for the installation of exhibits by January. So this was a building of nearly 1 million square feet made with wholly unprecedented methods of construction that went from design to completion in just 6 months, which is astounding. And among all the incredible innovations they developed in the course of realizing the Crystal Palace, the connecting piece was absolutely essential to their successes. And I think this one detail was the most impactful on accelerating the pace of construction. And Fox himself commented that he considered the connecting piece to be one of the most important points of the structure. And it undoubtedly was. So the connecting piece was the component used to join individual lengths of tubular iron columns and connect them to the prefabricated trusses and cast iron girders they'd support. So here on the left, you see a connecting piece on top of a length of column with workers fixing girders at its sides and ready to install another length of column on top. In a single typical cross-section of the Crystal Palace, these were the locations of connecting pieces, so 24 in this one section. In the building as a whole, there were 2,500 connecting pieces, which were manufactured in about a dozen slight variations. So it was the connecting piece that held together nearly the entirety of the building's structural fabric. And so the connecting piece itself, which you see here in yellow, was a cast iron component of standardized dimensions, produced with a high level precision and then honed with specially designed machine tools so it could be aligned with and bolted to sections of tubular column above and below. The connecting pieces were cast at Fox and Henderson's Ironworks in Smethwick, while the columns were cast at another foundry outside London, which specialized in the production of iron pipe and which was owned by the family of John Cochrane, who was Fox's chief assistant as on-site contractor. And perhaps most importantly, the connecting piece was specifically designed to be installed quickly by unskilled labor. On its sides, the connecting piece had a series of projecting ridges, which they referred to as snugs. And these snugs held the ends of cast iron girders, which you see here in the lighter orange, with one in elevation and the other cut in section extending toward you. And so these girders locked in place as a small projection cast on their undersides, the bits here in darker orange, slid into a groove on the lower snugs. So they sort of snapped right in to the correct location and alignment. 2 sets of wrought iron wedges, which they called keys, here you see them in red, were driven in by mallet into the joints between girders and snugs, securing the connection. And this process was incredibly fast and required little to no skill. And remember, the building was temporary, so these connections could be easily disassembled later. Now, this process of assembly and detail weren't based on any precedent in architecture, but rather they had grown from the prior experience of Charles Fox as an engineer, industrialist, and contractor. So as a teen, Fox was apprenticed to the inventor and mechanical engineer John Ericsson of Leeds, and he assisted him with experiments in early rotary engines. And along with the engineer John Braithwaite, they worked on the design and construction of the early steam locomotive, the Novelty, which you see here, and which was famously a leading competitor at the 1829 Rainhill Trials, which is an early racing competition of steam engines. By 1833, Fox began working for the British railway pioneer Robert Stephenson, and he spent 5 years as an engineer, contractor, and manager building the London and Birmingham Railway. It involved surveying, management, and the construction of rails, bridges, tunnels, and stations, including the Iron Roof at Euston Terminus. And in 1839, Fox went into partnership with the engineer Francis Bramah, and their company, Bramah Fox & Co., owned and operated their own foundries, produced commercial and industrial iron manufactures, and contracted on a range of industrial building projects. In the 1840s, Fox also patented a number of innovative designs for iron railway components, as well as new processes and machines for iron casting and working. And then in 1841, John Henderson, owner of a foundry in Smethick, was brought into the company. And when Bramah retired in 1845, the company was renamed Fox Henderson & Co. And by 1850, the business had grown substantially. Under Fox and Henderson, the Smethick works contained, quote, 70 forges and was stated to be the largest in the world. At this time, the firm was producing about 300 tons of castings a week and usually employed between 1,000 and 2,000 men. Now, with all this in mind, let's come back to the connecting piece and recall the language used to describe its mechanisms. So girders were secured to the connecting piece by way of snugs and keys. And these words, at least in the sense used here, were not architectural terms, but rather terms from other disciplines. So snug was a term of mechanical engineering and product manufacturing in iron. It appears in engineering literature from the 1830s on and refers to, quote, a projection or ridge cast on a plate or bolt in order to keep something in position or prevent rotation, end quote. And snugs were widely employed in manufactures assembled from multiple components in iron, so commercial products, machine tools, and so on. As for the term key, in building the Crystal Palace, it was employed in the same sense as the production of railways. In the construction of permanent way, which are the tracks on which locomotives ride, the key was a wedge, usually made of iron, which was driven between two elements to secure the relative position. And you can see those sorts of keys here in two different railway chairs. And in fact, Charles Fox had been granted patents for several railway chairs of his own design. This is one he patented in 1847. And if we take a closer look at one of these railway chairs, we see a mass-produced cast iron component designed with snugs, which will hold another component of the system, in this case, iron rails, which were then secured in place by driving in iron keys with a mallet. Now, if we take this railway chair, we rotate it 90 degrees, and we compare it to the connecting piece, again, we see two mass-produced cast iron components which serve to hold, by way of snugs, other elements of their respective systems, which are securely and firmly held in place by driving in iron keys with a mallet. So in mechanical principles, they are precisely the same. So for me, this is a translation of principles from one discipline to another, the transfer of knowledge from railway engineering and industrial product manufacturing into practices of building. And in both cases, we find the design of components, the design of details, which facilitate the efficient and indefinite expansion of their respective systems. And so I've said that the connecting piece reveals the ways its designers thought of the Crystal Palace less as a singular building and more as a system itself. And for me, this is most clear in the building's disassembly and afterlife. So at the end of the exhibition, the building was taken apart and it was moved to another site in Sydenham. The same parts were used, but it wasn't simply reconstructed. And in fact, Additional components were added. It was expanded in a number of ways. Both its length and width were altered. Additional arch vaults were added. Massing changes were made, and more. And when it was announced that this would be done, that the Crystal Palace would be moved and completely reconfigured or transformed in the process, the Builder, a popular technical magazine in 19th century England, published images which imagine the Crystal Palace's components reassembled into a 1,000-foot tall tower. Its system of components was imagined as redeployed in something wholly different and new. And remember, this is more than 30 years before we start seeing skyscrapers in Chicago. And when these images were published, Fox and Henderson commented on them. And they said, yes, in principle, a tower like this could be soundly constructed. So, in theory, one structural bay of the Crystal Palace could be replicated ad infinitum, and the building could be extended indefinitely. Fox and his team had taken Paxton's vision for the building and transformed it into a complex system of manufacture, labor management, and assembly. And they had done this by accounting for the entire process from manufacture to assembly to disassembly and beyond, and designing it into a powerfully instrumental set of construction details. And it was this recasting of the building as a system of rationalized, optimized, and economized details that I think made the Crystal Palace's very existence possible. Thanks for listening.
Thank you, Eric. I love the Crystal Palace. That is one of the coolest projects of old, and really a forerunner to the whole concept of design build. Definitely was design build. Anyway, I really appreciate that. We'll don't see any questions in right now. Do you, Alicia? No questions? Okay. What we're going to do then is we'll shift over now to detailing a post-war future. Homer Rissman's unbuilt structural expressionism in 1950 Chicago. Introducing Susan Singh is an architecture PhD candidate at the University of Texas at Austin and an adjunct professor in architectural history at Thomas Jefferson University, hence they know each other. Her research interest lies in the intersection of history of building technology and modernism preservation. She is writing her dissertation, quote, Interpreting Structural Heritage, Evaluating the Role of Auguste Commandant's Early Experiences from 1934 to 1950 in the Evolution of Pre-Stressing Technology. She is a graduate of the Weitzman Graduate Program in Historic Preservation at the University of Pennsylvania, as well as the University of Illinois Urbana-Champaign's Civil Engineering program. So Susan, take it away.
Thanks, Peter. Hang on 1 second. Let me share my screen. Okay, I think we're up. Okay, I should preface this talk just first by sharing that this work is actually not related to my dissertation research work, but you could call it sort of a fun side curiosity that I kept in my pocket over the past couple of years and was thinking this seems to be the perfect audience to share my thoughts with. And so what I'm presenting today revolves around one small detail. One detail for an exposed reinforced concrete column that I rather serendipitously came across while conducting archival research on an unrelated research project, but for the same architect, Homer Rissman. The detail was actually so small and easily overlooked that, in all honesty, I missed it upon first passing. I actually only caught it from my hotel room at night, zooming in on the hundreds of photographs that I took of drawings from the files of that day. It was also the date that was penciled in the corner, June 1950, which made me pause, thinking I might have found something really ahead of its time. Now, it's my understanding that Mies van der Rohe is typically credited with pioneering the technique of using fully exposed concrete structural framing techniques for high-rise apartment design in the US during that post-war period. But after seeing these drawings, what I became curious about was a little bit more general. How, where, and when exactly did this gain traction, eventually becoming accepted as mainstream? So one possible entry point is through the work of Homer Rissman, who was a much lesser known figure in the American modernism story, but who curiously was also a student of Mies at the Illinois Institute of Technology from 1943 to 47. One second. There we go. Now, I have a personal particular strong interest in looking for historic lines of influence within structural form. So here it makes quite a bit of sense to start by looking at Rissman's education at IIT, where he was undoubtedly shaped by the Bauhaus in exile style of teaching, so to speak. Mies's reputation as a leader of modernist design is well established, but we often overlook the most direct influence he must have had on his closest acolytes. And a rather select bunch they were by default. During the years of World War II, with many young men serving, the typical class size was often no more than a dozen gentlemen and sometimes down to only about 6. Although I was able to determine the courses that Rissman took and the respective instructors, without much more information, I realized, unfortunately, I may never know his exact relationship or exchanges with Mies. However, we can learn what construction detailing meant to Mies in his own words and attempt to extrapolate a probable pedagogy. For example, in the article Architectural Details in the October 1963 copy of Architectural Record, Mies explains, quote, "Construction is the truest guardian of the spirit of the times because it is objective and it is not affected by personal individualism or fantasy. The idea of a clear construction is one of the fundamentals we should accept." We can talk about that easily, but to do it is not easy. It is difficult to stick to this fundamental construction and then to elevate it to a structure, unquote. So as a historian, it's also worth looking at Mies's design work, specifically his first project working with developer Herbert Greenwald, the Promontory Apartments in Hyde Park on Chicago's South Side, designed and constructed from 1946 to 49. This was Mies's first high-rise construction, and maybe more importantly, the first to entirely expose its concrete frame. Mies emphasized the tectonic expression with step-back columns, what Siegfried Giedion called in Space-Time and Architecture a, quote, musical articulation to the whole facade, unquote. More importantly, though, with the Promontory Apartments, Mies set a groundbreaking precedent, signaling to other architects that the moment had arrived for embracing minimalist design, for middle-class, high-rise apartment living in particular. By fully exposing the concrete frame and eliminating ornamentation, he demonstrated how simplicity and economy could make comfortable mass housing a reality. Now, fast forward 1 year to 1950 to a subsequent development work of Mies with Greenwald, 2933 North Sheridan Road on the north side of Chicago. This is a really unusual building, as it is often relegated to a mere footnote in history, namely overshadowed by the simultaneous design and construction of Mies's masterful steel constructions, 860 to 880 Lakeshore Towers, and the Farnsworth House. So conceptually, 2933 is actually very similar to the Promontory Apartments. Affordable, comfortable high-rise apartment living aimed for the middle class, featuring an identical expressive concrete frame with stepped columns. However, here, Mies went further by removing the spandrel section and extending the glass framing entirely from floor to ceiling. This now brings us back to his student, a rather precocious 27-year-old Rissman, whose work was developing, for some reason, just 1 block over on Sheridan Road in parallel to Mies's. Rissman capitalized on opportunities in that post-war environment, namely the need for rapid economical housing solutions. He operated primarily as an architect developer, designing a series of 4 experimental concrete framed townhome complexes. Rissman invested his own money toward these small iterative projects, and always needing to be attuned to market demands and desires, he would have keenly been aware of where the public sentiment stood with regard to modern materials for residential applications. Thus, in his realized work, we can see where his vision was accepted, or conversely, in his unbuilt work, where acceptance may have been more hesitant. For context, while the larger 2933 North Sheridan was still under construction, Rissman had already completed this first concrete residential experiment, and it was notably the first completed construction in the entirety of this East Lakeview Nook after World War II. So this is his preliminary sketch from 1949. And as it stands today, with some modifications from various owners over time. But these first townhomes show that for Rissman's early experimentation with concrete construction, he used concrete block and precast concrete girder structural framing. Interestingly, though, for this first construction, Rissman chose to conceal the concrete framing behind a limestone and clapboard street-facing facade, not yet ready exactly to expose the structure. And my conclusion that I've reached after investigating all 4 townhome complex constructions from 1950 through 1953, his designs really kept evolving to continually expose more and more of the identical precast concrete girders that were being used. At first only visible at the rear patio, but later even at the street-facing facade, albeit painted black for a little bit of camouflage. So while researching Rissman's townhome work within this early Chicago portfolio, I discovered some amazing overlooked drawings for this mid-rise apartment building of today's topic. In the summer of 1950, Rissman had the 7-story, 8-bay building for 430 West Wellington on the boards. The design clearly shows Mies's influence of minimalism. Although it appears unassuming at first, this building actually signals a broader, albeit quieter, architectural current. The drawings showed something really curious. Here, Rissman included fully exposed concrete columns and girder details, structurally expressive, and in looking retrospectively, they were really quite far ahead of their time. So this is such a small detail, you can see how I nearly missed it. But if you look here at the exterior exposed concrete column detail, Rissman has taken Mies's concept, but inverted it so that the stepped feature is actually at the rear portion of the column. In order to fully express this, he recessed the facade plane, which leaves a small void space. And I think at most it was about a 1.5 feet. It's not too much, but it increased in depth as the eye travels up the building. And again, here we see it on the right, but in section detail. The architectural articulation is similar for the rear facade, but there, interestingly, he used brick masonry infill to accentuate the geometries. And a second unique feature of the design I'd like to highlight, the lot that it was situated on was a typical one for Chicago, very narrow at 25 feet, yet deep all the way through the alleyway. And unconventionally here, Rissman rotates the building entrance 90 degrees from normal street-facing orientation, turning the main facade toward a narrow courtyard for more privacy. Now, this side elevation that you see is the one that actually would be facing the public street and sort of helps to hint at the emphasis that he wanted to create for this unique oblique view of the concrete structure. In taking a deeper look, I noted that it was not just an exposed column, but in recessing the facade, Rissman exposed the girder connections at each floor level as well. And it's a little bit difficult to make out, but the section detail shows a typical girder extending beyond the recessed facade plane and sort of grabbing the column in what I have described as a lobster claw. Now, this may seem like a minor detail, but it really speaks volumes about his approach. He's further pushing boundaries of tectonic expression by using the structure as an architecturally aesthetic tool. More importantly, Mies's introduction of a design innovation at Promontory Apartments then tasked further architects with diffusing the idea and ultimately making it accepted. This societal shift appears to have happened only gradually, and yet these drawings show that Rissman was one of the first to take on the challenge of manipulating a concrete exterior in this way. To understand whether Rissman's design was part of a broader emerging trend, I tried investigating potential precedents that might have influenced his thinking, even hybrids where social forces sought economy while beginning to accept structure as an aesthetic form. And it just so happens that while researching one of Rissman's townhome constructions, you can see in the foreground, I happened to notice a mid-rise residential building in the background of a construction photo, located in the rear along Berry Street. And I noted the exposed concrete frame and brick infill at the non-street facing elevations. When I looked to the street facing facade, I realized this was a great example of a hybrid, hesitant to fully break free from traditional ornament. But built during the Depression in 1936, one can see the economical use of exposed concrete block ornamented with some decorative cast stone and then brick masonry, a stepping stone to the future abandonment of ornament and the acceptance to come shortly of a new structural aesthetic. Now, this example sparked my curiosity whether there were other signs shortly, maybe before the war, that would indicate a trajectory of this acceptance to come. And due to the scarcity of new construction during the war, I decided to review the pre-war designs, namely looking to pavilions at the 1939-40 World's Fair in New York, because designers were typically motivated to use cutting-edge concepts. And I found this intriguing possible precedent, the Brazilian Pavilion by Niemeyer, with a recessed facade plane and exposed concrete columns. Though much smaller, it did create a similar architectural effect by splitting the planes to articulate the structure. Next, I looked to back issues of progressive architecture from the initial post-war years to see if I could spot any undercurrents. From the January 1946 issue, this image, interestingly, is highlighting the progress which elapsed while architects may have been away at war, namely in the form of, quote, fresh new structural freedom, end quote, that exposed concrete afforded. Or possibly this concept sketch for the Philadelphia Psychiatric Hospital by Stoneroff and Lou Kahn, which includes a slanted glass facade revealing structure aesthetically, a la Peter Behrens' modernist AEG factory masterpiece. By 1947 issues, I discovered an advertisement by the Portland Cement Association displaying an undated Hugh Ferris concept drawing with rather expressive, exposed, and even pointy concrete pylons. An ad that touts the economy of using concrete, but more importantly, specifically called out such use for apartment houses. Now, unlike Mies, who benefited from the support of prominent developers and institutional backing, Rissman was just an independent and, might I add, very young architect builder navigating real-world constraints. His innovative proposals had to survive the filter of the public, not to mention investor acceptance, at a time when exposed concrete had not yet gained acceptance as a residential material. As such, his Wellington work reflects not only the promise of a new design paradigm, but also the challenges of propagating them without the weight of a well-known name. Still, it's telling and instructive that figures like Rissman were already indeed at least testing out the idea. Noteworthy are not only designs successfully constructed, but what is ultimately not built. In the case of Rissman's post-war experimentation, he was young, daring, and was trying his hand at all types of constructions. Those projects larger in scale than the townhome complexes did not become realized. And to me, this indicates that there was possibly not a consensus yet accepting this novel approach by a little-known designer presumably resulting in a lack of financial backing. Now, I speculate this because what was ultimately built at the site still stands today. Apparently, Rissman's proposal lost out to another architect's design, one for a set of townhomes constructed with rather traditional masonry and wood framing. Seeing that Rissman was at the leading edge of this trend in 1950, I wanted to track how this design approach eventually became evident in the mainstream over the subsequent years. And the first built example that I could find in Chicago was a residential high-rise building at 5740 North Sheridan by J. Marion Goodnier, completed in 1962, approximately 10 years after Rissman's mid-rise design. But here we see the exposed slab diagonally extending at the rounded column, possibly more easily seen in the raked light shot from the right-hand image I'm sharing. Similarly, for commercial high-rise construction, in the same year, we have Bruce Graham of SOM, who completed the Hartford Insurance Building in downtown Chicago with a fully extended slab, recessed glass facade, and a more monolithic, chunkier sculptural quality of the column detailing. A short time later, in 1963, we see an even more simplified version of Graham's design for the BMA Tower in Kansas City. By the 1960s, one starts to see similar commercial copycats pop up across the country, with normalized acceptance of visible concrete framing. So the next time you encounter a building with exposed concrete structure, for instance, a more dramatic example like the 1975 Federal Building Tower by Toombs, Amisano, and Wells in Atlanta, I hope you'll recall this talk and remember how these elements reflect an evolution of embracing modernity. What we now take for granted was once groundbreaking, and it was architects like Rissman who dared to test its diffusion. Thank you.
Thank you, Susan. Very interesting. It's crazy because I recognize some of these buildings, especially this last one in Atlanta where I went to school at Georgia Tech. It was quite the thing. All right. Any questions at this point, Alicia?
Yes, so Eric, there's a question in the chat from Art Hunkle. And he's asking, and you indicated you might answer it live. I see you've answered several of the questions sort of in the Q&A already. But the question is, did the connector piece have any influence on Eiffel and his tower in 1880s France?
Yeah, I tried to answer that, but for some reason it wouldn't let me. I guess I indicated I'd answer it live. Yeah, so it's funny, the influence of it was quite muted for a long time. I don't know that it had that much of an effect on Eiffel. Also, current research attributes really the Eiffel Tower and its innovations to two employees in his office, not to Eiffel himself. There's been some good work on that recently. I'd say that within France more broadly, in the second half of the 19th century, there was a very, I think, a rising current of this kind of like focus on the hybrid of engineering and science. I was at certain schools there too, like Centrale. And I think that was more an outgrowth of the environment there. Where the Crystal Palace really seemed to have more of an impact would be, I think, on the thinkers of the 20th century that are associated with modernism. So like Siegfried Giedion was somewhat obsessed with the Crystal Palace, and he wrote about it as like the moment when modern architecture began. Another notable practitioner was Konrad Wachsmann, who was also obsessed with the Crystal Palace, and he really cited it as the possibility for creating a universal detail that could be applied in all sorts of different situations. So yeah, I think as far as its immediate impact, it was really muted. Its immediate impact was not very great, I think, in England or in France at the time.
Great. And then we have a question for Susan from Ann Doherty, which was, what role did PCA play beyond futuristic designs in the promotion and diffusion of reinforced concrete? Or I'm sorry, of exposed concrete?
Sorry, who was this again?
It was a question from Ann Doherty about what role did PCA play beyond futuristic designs in the promotion and diffusion of exposed concrete?
Oh, I'm not sure. Yeah, I definitely was just looking for visual examples as I was like plowing through the old journals. Um, I'm not sure I have any specific other examples from PCA, but they certainly had a vested interest in promoting any and all constructions. Um, so.
Indeed. So Eric, I have a question or a comment, because the one interesting thing about the Crystal Palace is it sort of triggered a lot of innovation in some other industries, particularly the glass industry. As I seem to recall, the development of these crystal houses and stuff like that required a transformation of how glass was made, primarily in the northern part of the UK,
Hmm.
and how it had to be shipped down for the Crystal Palace. I don't know if you can expand on that at all.
I don't know much about that. I mean, I do. There was a question dropped in the chat about the glass. And the glass was very interesting because, so it was cylinder glass, produced by workmen in a rather traditional fashion. And the comment in the chat was about it being one of the limiting factors. And in fact, it was. It was actually one of the first things that they determined is that to produce the amount of glass that they needed, that the maximum dimensions of it could be just over 4 feet long. So they calculated that based on a panel that was about 4 feet 1 inches long, that they could, in the region for a roof, use three sort of bays of, glass together. So six sections of glass, and it would lend itself to a 24-foot structural module. So the entire structural module of the building was reset. Initially, it was, I think, around 20 feet. It was reset at 24 feet to economize glass production. As far as that goes, I'm not sure when production moved. I guess you're referring to like the shift from cylinder to like float glass.
Yeah.
Yeah, yeah. I don't know much about the history of float glass. Um,
Well,
yeah.
something for the subject of a
Hmm.
future presentation, I would assume. So, and Susan, I know, looking at these exposed concrete structural forms, those would have a very, very difficult chance of survival in today's energy economy, especially in the colder climates, with the inability to stop the cold from coming in through the concrete right into the perimeter of the floor of the unit. So have you seen anything about that, or how people have retrofitted these old structures at all?
I know that the bigger thing was just the floor to ceiling single paned window detailing. Many have replaced the windows. I know very few of the original windows still exist. I don't know if you saw in that one photograph of the original
Yeah,
townhome complexes, but they were all sort of experimental and certainly in that respect. And many of them have not survived.
yeah,
Unfortunately, it's created sort of a hodgepodge with each individual owner choosing a different solution. So architecturally, it doesn't have that conformity anymore.
right. No association to control the the exterior image. Although interestingly enough, in Chicago, there is a fairly recent high rise that was built with undulating um, floor plates, post-tension floor plates on the exterior of the glass plane, which really has kind of an interesting overall effect. But I still wonder about that in Chicago, for how that feels on the inside of the building. Anyway, all right. Any other questions out there, Alicia?
There's one more in the Q&A, and I know Eric, you partially answered it in the chat, but I'm not sure if all the panelists or if all of
Yeah.
the attendees can see that. The question is from Gregory Dreiser, and it's the Crystal Palace connections were known to have failed very seriously due to expansion contraction. Can you comment on this, and also can you discuss the role of wooden components in the Crystal Palace connections?
Sure. I have not read reports of the components failing during the Great Exhibition. I don't believe there were any serious failures then. I mean, when it was moved to Sydenham, it was there for 80 years. So that's a different story. I haven't followed the whole history of it at Sydenham, and I know there were issues there, which obviously culminated in a fire in 1936, which destroyed the building. As far as expansion contraction, so there was another question about some of the thermal conditions there. I mean, the building was ventilated. One of the detailed drawings that I showed was of a louvered system that was on the lower portion of the building. There were several places in which it was ventilated, and it wasn't really intended to be a sort of greenhouse. It wasn't intended to have any sort of.
Oh, you went mute, Eric.
Can you hear me?
Yep.
Okay. There were issues with it overheating. One of the things that they tried to do to accommodate that is they actually used a kind of canvas above a lot of the ridge and furrow roofs as a shading device. So I mean that was an issue. But again, other than some reports of during the Great Exhibition, that is during the actual event, there were reports that I've read of workmen having to check and tap in loose wedges, loose keys at points. As far as the role of wood components in the Crystal Palace, I also have read at times. I don't know what the logic was, but there is a phrase in one text that I've read about those connections that the keys that they used for the connecting pieces were iron and sometimes wood. But I'm not sure why or where, and I haven't found any other commentaries on it. Aside from that, the most notable part that was made of wood was the Paxton gutter, which was something that was employed by Paxton at the Lily House. It was a really innovative gutter that was part of the structure of the ridge and fur roof, and then it collected the water runoff both on the underside of the glass and from rain on the exterior. But they sort of remade it through serial production at the event at Hyde Park, where they built camber into the components with tension rods, and there are all sorts of other hybridized components to allow it to drain to the columns. And actually, all the columns are hollow, and the water runoff drained through the columns down into the foundation of the building, where it was channeled to a pump house that was, I believe, at the southern end of the site.
If anybody goes out to Hyde Park today, you can still find the corner of the Crystal Palaces. They've been marked into the turf, which is now just an open park field. So kind of interesting. All right. Well, in the interest of time, we have a last sort of surprise for you here. I'll share my screen. So, as I promised you, we have a happy birthday celebration to, hang on a second, the Erie Canal, born in 1825 and still living. So in 1811, a commission studying this potential for the canal concluded what you see here on the screen, basically that it's going to be a miracle for economic development. And it truly was. Actually, the potential for the canal was started as early as 1808, where in the Finger Lakes region of New York State, a farmer named Jesse Hawley proposed or wrote some essays about the need for a canal. There obviously were a lot of lakes and rivers in the area, but that sort of spurred on some thinking by a number of very well-known political types to create a canal. On this map, here's the Hudson River, which was connected also by a canal to Lake Champlain. And then the original proposal was to think, well, maybe we should put one to Oswego, New York, right here. It'll be a lot shorter than going all the way across to Buffalo or just north of Buffalo. But the fear was quite convincingly that any ship that would come through this canal and connect to Lake Ontario, which hadn't existed at the time, would end up in Montreal instead of New York. So they decided we need to do this whole thing. But it was really a challenge. The Welland Canal, by the way, was after the Erie Canal was built. The Welland Canal connected Lake Erie and Lake Ontario and has been rebuilt multiple times and still exists today. But this statement about the Erie Canal and what it did for the economic development in the area was not to be lost. And it was really championed by former governor, former mayor of New York City, DeWitt Clinton. And he was sort of the mastermind, the big driver behind the Erie Canal. He tried to get funding from Thomas Jefferson, who just thought that this would rob the young country's treasury. But instead, the War of 1812 came around, so that sort of delayed the construction of the Erie Canal and also its potential funding. So he tried again, and Madison was the second person to actually veto a bill that would have paid for the Erie Canal through government funds, because it would have benefited the government as a whole. But undeterred, DeWitt Clinton decided to fund this as New York State, out of New York State funds, and build it for the benefit of connecting New York City to the Great Lakes. And that Clinton started construction on this, what was called the Clinton's Ditch, in July 4th of 1817. Now, the end of the construction in 1825 sort of terminated at what they called the Niagara Escarpment in western New York, near Buffalo, which is basically the same escarpment that forms Niagara Falls, where they had to put what they call 5 step locks in series up from the lower level of the canal up to the higher level of the canal that would eventually drain into the Niagara River. So basically the canal itself was started in 1917 and opened in 1825. So it took 8 years to build the entire length. Now, I understand that it was open for part of its length as it was being built, basically from east to west. But the amount of rock and that basically had to be taken out of this ditch was actually significant. And the whole event was celebrated in 1817 by Governor Clinton, who was governor at that time, who boarded the Seneca Chief, which is right here, a steamship that was able to navigate the entirety of the canal, starting in western New York, all the way through for over 8 days to get to New York City. And he brought with him a bucket of water from Lake Erie and then dumped it into the Hudson Bay right by Sandy Hook. Now, if you go out to the Lockport area, if you ever have a chance to visit Lockport, I recommend highly that you visit the locks. Now, there's been multiple reconstructions of the Erie Canal over the years to accommodate larger boats, and I don't need to go into all the details of these, but this is an example of the restored lock gates at one of the 5-step locks in Lockport. This shows it from the lower view. Again, these gates would close and this would all fill up with water and raise the boat. This is a replica that they have out there right now, which is what sort of the first longboats were that navigated the canal. The canal was originally designed as 40 foot wide and 4 feet deep and 363 miles long and rising over 675 feet over its length. It originally had 83 locks when it opened. That's a lot of locks, all right? But it was enlarged in 1835 and in 1862, which reduced the number of locks to 72, which also, it should be noted, every time you reduce the number of locks, you increase the speed at which somebody can transect the lock as you go across. And this is what it looks like when the gates are closed. And then there's that traditional longboat, which is kind of interesting that today, you can kind of see in the background here, the modern canal is a new lock that's over on the right side that was built next to the original 5-step lock. And when they widened the overall canal to accommodate larger boats, It was reduced to what it is today, only 35 locks to get from Lake Erie to New York Harbor, or actually to the Hudson River. It had enormous impact. This is just sort of an example. A lot of towns grew up along the Erie Canal. When it opened, it towed boats at about 4 miles per hour along a towpath. For comparison, a horse and wagon at that time could pull a 2-ton load. So if you just took a horse and wagon from wherever to New York, it could only take 2 tons. The longboats at the time, or a barge, as they later developed, weighing 50 tons, could move down the canal, obviously a lot quicker. And the canal was soon carrying twice the volume of cargo when it was built as the Mississippi River was at the same time. Of course, there wasn't as much development along the Mississippi River in those days. So this summer, I rode my bicycle along the Erie Canal again and was reminded as I went through Lockport that it was the 200th anniversary of the Erie Canal, because they were having a whole bunch of celebrations all along the canal for the opening of the canal. Interestingly, when the canal was opened and Governor Clinton made that trek across the canal to New York City, his departure from the west was signaled by a cannon salute. So all the towns along the way would fire a cannon when they got word that DeWitt Clinton had left. And it took, I think, something like 20 minutes for that signal to really reach New York City or something like that. It was kind of an interesting way to signal how that would work. But that's just to say, I think we owe a lot to the Erie Canal for having had such an impact on our economic development and development even to the west and even up to Minnesota, where I am, where Duluth, being one of the westernmost ports on the Great Lakes region, could still sail through the Erie Canal to New York City. So with that, happy 200th birthday to the Erie Canal. So to our presenters and the producers, I want to thank all of you for making this presentation possible. I'll leave this slide up right now. Eric and Susan's email is here. If you have any further questions of them, I'm sure they would be willing to answer. I would suggest, if you're not a member of the Construction History Society, now's the time. All right. I hope you've enjoyed this presentation. You can visit us at constructionhistorysociety.org, and we will be having our biennial in Mexico City in 2026. So the first time we will venture out of the United States down to a foreign country to host our conference event. So with that, any final comments from our team? All right. Well, to everybody, thank you, and enjoy the day and enjoy your history. Thank you.